Okay. We're recording? We're recording. All right, so I left you guys on Friday with this idea, and we kind of started discussing what this would mean in context to the scenario, and I wanted you guys to finish it by actually using a left and right Riemann sum to approximate those definite integrals. But one of the ideas that we talked about back at the beginning of the unit when we were first starting to talk about the idea of integrating the rate of change from a point A to a point B is that if we are integrating the rate of change, what we are finding is the amount of change. And we discussed a few different reasons why that was and why we were seeing that. But now that we know the fundamental theorem, we can actually see a little bit better why that is. Because if, in this case, R is the water that's being, the rate of the water being pumped into a tank. So we said that that represents the rate of change of the volume of the water with respect to time. So we could think of R as the derivative of W if W is the function that represents the volume of water in the tank. Well, then if we apply the fundamental theorem, if we're integrating R from 0 to 20, we're integrating the derivative of W from 0 to 20. And the fundamental theorem says that if we integrate the derivative, we end up with the function evaluated at 20 minus 0. So W of 20 would be the amount of water in the tank at time 20. W of 0 would be the amount of water in the tank at time 0. And when we take the difference, we're actually finding the amount of change during that time interval. So the fundamental theorem kind of backs up what we were looking at before when we were first approximating these definite integrals using Riemann sums or area formulas to find the exact value. So you guys were supposed to use the data from the table and 4 subintervals to actually approximate that integral. First, we're using a left Riemann sum. If we're doing 4 subintervals, then we're going to do 0 to 5, 5 to 9, 9 to 15, 15 to 20. So the integral from 0 to 20, r of t dt, if we're using the left endpoint, for our first subinterval, we have a width of 5, and the left endpoint function value would be 14. For our next subinterval from 5 to 9, we have a width of 4, and our left endpoint function value would be 18. For our third subinterval from 9 to 15, we have a width of 6, and again, we're using the left endpoint, so that would be a function value of 20. And then finally, for our last subinterval, we have a width of 5, and our left function value would be 27. So we have 5 times 14, which is 70. 4 times 18 would be 72. 6 times 20 is 120. And 5 times 27 would be 135. 5 and 2 is 7. 3, 4, 5, and 7 is 12, and another 7 would be 19. And then so 397. And because we're talking about gallons per minute, we're taking our width of our subintervals, which is minutes, and multiplying it times the rate of change, which is gallons per minute. So we end up with gallons, which makes sense because, again, if we're talking about the amount of change in the volume of the water, it would be measured in gallons if our rate of change is in gallons per minute. So during that 20-minute interval, the volume of the tank changed by 397 gallons. That doesn't necessarily mean that there's 397 gallons of water in the tank. Remember that if there was water in the tank when we began, that wouldn't be the total volume. But we know how much the amount of water changed by. Any questions about that? If we use a right Riemann sum to approximate the definite integral of r from 0 to 20, same width, but now we're using the right endpoint. So our first subinterval is a width of 5, And the height this time would be 18 because we're using the right function value. Our next subinterval is a width of 4, and this time a height of 20. Our next subinterval, still a width of 6, but now a height of 27. And then finally our last subinterval, still a width of 5, but now we have a height of 32. So we have 5 times 1890 plus 4 times 20 would be 80. Plus 6 times 27, let's see, 2, carry the 4, 162. And then we have, let's see, 0, carry the 1, 160. So then we got 2, 6 and 6 is 12, and 8 is 29. Carry the 2, 3, 4, 492. And again, that would be in gallons for the same reason because we're using the same units to measure. So our left endpoint gives us an estimate in the change of the volume being 397 gallons. Our right Riemann sum gives us an estimate in the change of volume being 492 gallons. That's a pretty big margin of error there. But if we have more information about the function, for example, if we actually knew the equation of RFG, the rate at which the water was flowing into the tank, we could find the exact amount of change and not just an approximation there. Do you have any questions?